Hello everyone, myself Prashant from BSc Chemistry Honours first year. Today we are gonna read chapter Structure and Bonding. There we go. The term organic compounds was originally applied to those compounds which are derived from living sources, plants or animal sources, while the term inorganic compounds was applied to those which are obtained from mineral sources. In the earlier days, it was assumed that the laboratory preparation of organic compounds was impossible. However, in 1828, a breakthrough was achieved when Wohler synthesized urea, an organic compound present in the urine of animals, from ammonium cyanate, which in turn was prepared from ammonium sulfate and potassium cyanate. In 1845, Kolb then synthesized acetic acid from inorganic sources, and thereafter synthesis of organic compounds began to occur at fast pace. Modern definition of organic chemistry. It is now defined as the organic chemistry of compounds containing carbon as an essential element. However, a few compounds of carbon like carbon monoxide, carbon dioxide, carbonates, which are organic by above definition, are studied in inorganic chemistry as their properties are entirely different from those of organic compounds. As the simplest organic compounds are hydrocarbons, which are made up of carbon and hydrogen, thus all organic compounds may be considered as derivatives of hydrocarbons. Therefore, organic chemistry may also be defined as the chemistry of hydrocarbons and their derivatives. Before studying the synthesis and structure of organic compounds and the mechanism by which the reaction takes place, a brief overview of certain fundamental concepts is being given in this chapter. Modes of hybridization, shapes of compounds. Definition upon the types of atomic orbitals involved in hybridization. See, a carbon atom undergoes following three types of hybridization in its compounds. First, sp3 hybridization. When one of the s and 3p orbitals hybridize, resulting in the formation of four identical sp3 orbitals which are arranged tetrahedrally in space, i.e. pointed towards the four corners of a regular tetrahedron, then carbon atom is said to exhibit sp3 hybridization. As such, the resulting shape of the molecule will be tetrahedral with a Bode angle of 109.28 degree. The orbital picture of sp3 hybridization is shown in figure. Here is the figure. sp3 hybridization is observed in organic compounds containing a single bond. Bonds formed by the overlap of hybrid orbitals are much stronger than that formed by the overlap of atomic orbitals. This is because of the unequal size of lobes of hybrid orbitals, by virtue of which greater area is available for overlapping and consequently stronger bonds are formed. Compare equal lobes of a simple orbital, unequal lobes of a hybrid orbital, larger lobes overlap to form stronger bonds. Second, sp2 hybridization. When one s and 2p orbital, 2px and 2py hybridize, resulting in the formation of three identical sp2 orbitals which lie in the same plane, oriented at an angle of 120 degrees from each other, then carbon atom is said to exhibit sp2 hybridization. As such, the resulting shape of the molecule is trigonal planar with the Bode angle of 120 degree. The orbital picture of sp2 hybridization is shown in the figure. sp2 hybridization, 2pz remains as such shape, type 3 sp2 hybrid orbitals, 2pz. sp2 hybridization is observed in compounds containing a double bond, as in ethylene. The carbon-carbon double bond is made up of a stronger bond, sigma bond, formed by the overlap of sp2 hybrid orbitals, and a weaker pi bond, formed by the sideways overlapping of two anhybrid p orbitals located perpendicular to the plane of hybrid orbitals. The rest of the sigma bond of ethylene molecule are formed by the overlap of sp2 hybrid orbitals of carbon atom with one s orbital of H atoms. Third, sp hybridization. When one s and one p orbital hybridizes, resulting in the formation of two identical sp orbitals which are oriented at an angle of 180 degrees from each other along a single straight line. Then carbon atom is said to exhibit sp hybridization. As such, the resulting shape of the molecule is linear with the Bode angle of 180 degree. The orbital picture of sp hybridization is shown in the figure. Here is the figure, you can see. Now, localized and delocalized chemical bonds. A localized chemical bond. When two atomic orbitals overlap to form a covalent bond, the resultant orbitals that are formed are known as molecular orbitals. The electrons involved in the bond formation are shared between the atoms and are now said to be the molecule, not individual atoms. The probability of finding these electrons in the molecular orbital is greatest in the region between the two nuclei. It is because of the concentration of these negatively charged electrons in the internuclear region. The two nuclei are bound together. For example, when two 1s orbitals of two hydrogen atoms overlap, the two electrons pair up and occupy the same molecular orbital. Such a molecular orbital is said to be localized, and bond so formed is known as localized bond. Here you can see the formation of hydrogen molecule. Delocalized chemical bond. Definition is the bond whose electrons are spread over the nucleus of more than two atoms is known as delocalized chemical bond. For example, consider 1,3-butadiene, a molecule with conjugated double bonds compound with alternate double bond and single bonds. Each carbon atom in 1,3-butadiene is sp2 hybridized, and all the three bonds hybrid orbitals of each carbon atom are used in the formation of sigma bonds, after which each carbon atom is left with an unhybridized p orbital, which are used in the formation of pi bonds. If the molecule is planar, the four unhybridized p orbitals may overlap as depicted in figure. Here's the figure you can see. Now, resonance. The concept of resonance was introduced to explain the structure of compounds which can be represented by more than one valence bond structure, which of each of which can explain some but not all the known properties of compound. The actual structures is said to lie somewhere in between the various possible conventional structures. The phenomenon is known as resonance. The various possible structures are called contributing or canonical structures, and the actual structure is called the resonance hybrid. The various contributing structures are represented by putting a double-headed arrow between them. The various contributing structures differ only in the relative position of electrons and not of the atoms. One of the most well-known examples of compound showing resonance is benzene. Benzene could not be assigned a single satisfactory valence bond structure which could explain all its properties. Therefore, it was proposed that benzene is a resonance hybrid of structures 1 and 2. Here are the structures 1 and 2. You can see this double-headed arrow between the two structures does not mean the molecule oscillates from one structure to another. It does not mean that molecule of benzene spends a part of its time as structure and rest of the time structure 2. Nor does it mean that some molecules of benzene have got structure 1 and other have got structure 2. Neither it implies that the mixing of formal letters structures. What resonance actually means is that the actual structure of benzene cannot be represented completely 1 or 2, but it lies somewhere in between the two and is called resonance hybrid. This concept thus applies that the resonance hybrid of benzene, the bonds linking the carbon atoms, would neither correspond to pure single or nor bonds, double bonds. Rather, all the bonds will be equivalent and intermediate between the single and double bonds. This fact has actually been confirmed by X-ray diffraction studies, which show that all the carbon-carbon bond lengths in benzene are the same, and in between the carbon-carbon pure single bond length and carbon-carbon pure double bond length. Some other example of resonance: carbon dioxide. Carbon dioxide is represented as a resonant hybrid of the following three contributing structures. The observed carbon oxygen bond length in CO2 is less than that of the carbon atom double bond length. This fact can be justified in terms of resonance. Carbonate ion. Carbonate anion can be represented as a resonant hybrid of the following three structures. A first look at the structures might lead us to conclude that the carbonate anion contains two carbon-oxygen single bonds and one carbon-oxygen double bond. But this is not so. Actually, it has been observed that all the carbon-oxygen bond lengths are equal length, and this fact can be explained on the basis of resonance. 1,3-butadiene. Conjugated dienes like 1,2,3 butadiene also show resonance. Carboxylic acid may be regarded as resonant hybrid of the following two structures. Because of the resonance, oxygen atom acquires positive charge and easily split off the proton. Thus, resonance helps to explain acidic nature of carboxylic acid. Conditions for resonance. The various contributing structures should differ from each other only in the positions of electrons and not in the position of atoms, and their state of hybridization must be the same. The various atoms involved in the resonance must lie in the same or nearly the same plane. Resonance or mesmeric effect. It is the process of permanent displacement of electrons in a molecule due to resonance or mesmerism. Unlike inductive effect, resonance or mesmeric effect is transmitted through pi electrons of the system. It operates in unsaturated compounds containing a suitable atom or group in conjugation with a pi bond or a set of alternate pi bonds. For this reason, it is also termed as conjugative effect. Definition: this kind of electron distribution is unsaturated compounds conjugated with electron releasing or electron withdrawing groups or atoms is called resonance or mesmeric effect. Resonance effects causes delocalization of electrons and gives rise to additional contributing structures due to withdrawal or release of electrons by the given group. For example, when carbonyl group is conjugated with a double bond, the carbonyl group exerts electron transfer towards itself pi electrons. Thus, the polarization of the carbonyl group is transmitted via the pi electrons of the carbon chain. Similarly, the lone pair on the nitrogen atom repels the pi electrons of the conjugated chain of amino compound. This delocalization of pi electrons due to the resonance or mesmeric effect results in the number of resonance structure which gives stability to the ions. Applications of resonance effect. Resonance effect helps to explain the stability and reactivity of the several chemical species as exemplified below. Low reactivity of vinyl and aryl halides toward nucleophilic substitution reaction. Explanation: the halogen atom in vinyl and aryl halides causes delocalization of electrons due to plus R effect, giving rise to additional contributing structures as shown. Here we can see the structures. Because of resonance, the carbon halogen bond acquires partial double bond character, as a result of which the halogen atom gets more firmly attached to carbon atom and is not displaced easily. This explains the low reactivity of vinyl and aryl halides as compared to alkyl halides towards nucleophilic substitution reaction. High reactivity of allyl and benzyl halides towards nucleophilic substitution reaction. Explanation: allyl and benzyl halides readily ionize to give resonance stabilized carbocations as shown. Here we can see the structures: benzyl chloride and resonance stabilized benzyl carbocation. Because of resonance stabilization, allyl and benzyl carbocations are readily formed, which are then attacked by nucleophiles, and reactivity of allyl and benzyl halides towards nucleophilic substitution reactions is greater than that of the alkyl halides, which give rise to carbocations which are not stabilized by resonance and hence are not easily formed. Acidic nature of carboxylic acid. Explanation: both carboxylic acid and carboxylic iron are stabilized by resonance as shown. Hyperconjugation, no bond resonance. The concept of hyperconjugation was put forward by Baker and Nathan on the basis of the following observation. Generally, the electron releasing inductive effect of different alkyl groups attached to a saturated carbon follows the order. However, the above order is inductive effect get reversed when an alkyl group is attached to an unsaturated system such as a double bond or a benzene ring. In such cases, electron releasing effect operates by a different method than in inductive effect. The electron releasing effect is explained by assuming that the sigma orbital of the carbon hydrogen bond overlaps with the adjacent pi or p orbital. For instance, consider the delocalization of electrons in the alkene. Delocalization involves overlapping between sigma orbital of a carbon-hydrogen bond of the alkyl group and the pi orbital of carbon-carbon bond. As a result of such overlap, the four atoms are bound together in some extent. The displacement of the electron pair of the carbon hydrogen causes a partial positive charge on the hydrogen atom without the actual proton release. The above situation may be taken to mean that the given alkene is a resonant hybrid of canonical forms such as 1 and 2. Inductive effect. The electron cloud in a sigma bond between two like atoms in uniform. For example, carbon-carbon covalent bond in alkanes, the sharing of electrons is a symmetrical between. However, if one of the atoms is replaced by a more electronegative group or atom such as halogen, the electron cloud between two unlike atoms is no longer uniform and is displaced towards the more electronegative atom. As a result, the atom X requires a slight negative charge and carbon atom is a slight positive charge. This permanent state of polarization is called inductive effect. The inductive effect is represented by a arrowhead in the middle of the covalent bond pointing in the direction of electron displacement. Now the positively charged carbon 1 exerts an attractive influence upon the electron pair shared between carbon 1 and carbon 2 due to the resultant electron displacement towards the carbon 1. There is a development of positive charge on carbon 2, but the charge on carbon 2 is smaller than the charge of carbon 1. The positively charged carbon 2 then attracts the electron pair of the bond carbon 2 and carbon 3, thereby making carbon 3 also very slightly positive charged. The progressive decrease in the inductive effect is consequent decrease in the magnitude of charges with increase in distance is shown by decrease in the number of arrows. Definition is this process of electron displacement along the chain of atoms laid through sigma bonds due to the presence of polar covalent bond in a molecule is known as inductive effect. Application of inductive effect. Comparison of relative acidic strength of organic acids. In aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate ion and hydronium ion as shown. The strength of an acid is generally expressed in the terms of its acidity or delocalization constant Ka, which is defined as follows. Comparison of resonant and inductive effect. Resonant effect. Resonance effect operates only in unsaturated systems in conjugated system, while inductive effects operates even in saturated systems. Presence of unsaturated is not an essential condition. Second, it involves displacement in non-bonding and pi electrons. In inductive effect, it involves displacement of sigma electrons. In resonance effect, it leads to delocalization of electrons, while in inductive effect, no delocalization of electrons takes place. In inductive effect, during localization, electron pair is completely transferred, leading to the development of full positive and full negative charges. In inductive effect, electron pair is only slightly displaced from its position, leading to the development of partial positive and negative charges. In resonance, it is transmitted over large distances without any change in intensity. In inductive effect, it decreases sharply with increase in the distance and operates over only short distances. Next, comparison of inductive and electromeric effects. In inductive effect, it is a permanent effect which involves a mere displacement of electron. And electromeric effect, it is a temporary effect which involves the cleavage of multiple bonds and completely transfer of shared pair of electrons to one of the atoms. In inductive effect, there is only a slight distortion in the shape of molecular orbital containing the displaced electrons. The electrons never leave the molecular orbital. In electromeric effect, the electron pair of multiple bond leaves its molecular orbital completely and gets transferred to one of the atoms. In inductive effect, the only requirement for this effect is the presence of some polar bond in a molecule. It is not necessary for the molecule to contain a multiple bond. In electromagnetic effect, this effect can be exhibited only by molecules containing at least one of the multiple bond which may or may not be polar in nature. In inductive effect, it does not require an outside attacking reagent, and in electromagnetic effect, it takes place only under the influence of an attacking reagent. In inductive effect, it involves partial separation of charges, and in electromagnetic effect, it involves complete separation of the charges. Van der Waals interactions, intermolecular forces. Intermolecular forces are the forces which operate between molecules of the same or different substances. Depending upon the nature of the molecules, these forces are of different types. In case of compounds containing polar covalent bonds, intermolecular forces of attraction arise due to the dipole-dipole interaction. In such cases, the negative end of the one molecule will attract positive end of the another molecule. On the other hand, non-polar molecule substances such as oxygen, nitrogen, and methane exist in the gaseous state in the form of individual covalent bonded molecules. But at even the substances as well as the noble gas undergo condensation at low temperature to liquid and solid state. This observation led Van der Waals up Dutch scientists to conclude that there must also exist same weak intermolecular interaction between such a non-polar molecule. Subsequently, these forces came to be termed as Van der Waals forces of attraction. Van der Waals forces may be defined as the weak forces of attraction between non-polar molecules which arise from the movement of electrons in atoms and molecules. These forces are very weak, as is evident from the fact that the noble gases have very low boiling points. Origin of Van der Waals forces. Consider two helium atoms very close together. Ordinarily, in each atom, the negative charge of electron is symmetrically distributed around the nucleus, but since the electron moves about freely, it is possible for a particular instant of time that the electron distribution in an atom becomes somewhat with each other. The temporary separation of positive and negative charges produces an instantaneous temporary dipole. Here we can see the structures, and here are some questions for practice. You can see, and our lecture for this chapter is complete. So that's it for today's video.